This photo shows a large open newsroom with enough space to seat about 200 employees. Figure 1. We encounter statistics in our daily lives more often than we probably realize and from many different sources like the news. Credit modification of work new office by Phil Whitehouse / Flickr, CC by 20. You are probably asking yourself the question, when and where will I use statistics? If you read any newspaper, watch television, or use the internet, you will see statistical information. There are statistics about crime, sports, education, politics, and real estate. Typically, when you read a newspaper article or watch a television news program, you are given sample information. With this information, you may make a decision about the correctness of a statement, claim, or fact. The statistical methods can help you make the best educated guess. Since you will undoubtedly be given statistical information at some point in your life, you need to know some techniques for analyzing the information thoughtfully. Think about buying a house or managing a budget. Think about your chosen profession. The fields of economics, business, psychology, education, biology, law, computer science, police science, and early childhood development require at least one course in statistics. Included in this chapter are the basic ideas and words of probability and statistics. You will soon understand that statistics and probability work together. You will also learn how data are gathered and what good data can be distinguished from bad. The science of statistics deals with the collection, analysis, interpretation, and presentation of data. We see and use data in our everyday lives. In this course, you will learn how to organize and summarize data. Organizing and summarizing data is called descriptive statistics. Two ways to summarize data are by graphing and by using numbers, for example, finding an average. After you have studied probability and probability distributions, you will use formal methods for drawing conclusions from good data. The formal methods are called inferential statistics. Statistical inference uses probability to determine how confident we can be that our conclusions are correct. Effective interpretation of data inference is based on good procedures for producing data and thoughtful examination of the data. You will encounter what will seem to be too many mathematical formulas for interpreting data. The goal of statistics is not to perform numerous calculations using the formulas, but to gain an understanding of your data. The calculations can be done using a calculator or a computer. The understanding must come from you. If you can thoroughly grasp the basics of statistics, you can be more confident in the decisions you make in life. Probability. Probability is a mathematical tool used to study randomness. It deals with the likelihood of an event occurring. For example, if you toss a fair coin 4 times, the outcomes may not be 2 heads and 2 tails. However, if you toss the same coin 4,000 times, the outcomes will be close to half heads and half tails. The expected theoretical probability of heads in any one toss is 1 or 0.5. Even though the outcomes of a few repetitions are uncertain, there is a regular pattern of outcomes when there are many repetitions. After reading about the English statistician Carl Pearson, who tossed a coin 24,000 times with a result of 12,012 heads, one of the authors tossed a coin 2,000 times. The results were 996 heads. The fraction 996, 2,000 is equal to 0.498, which is very close to 0.5, the expected probability. The theory of probability began with the study of games of chance such as poker. Predictions take the form of probabilities. To predict the likelihood of an earthquake, of rain, or whether you will get an A in this course, we use probabilities. Doctors use probability to determine the chance of a vaccination causing the disease the vaccination is supposed to prevent. A stockbroker uses probability to determine the rate of return on a client's investments. You might use probability to decide to buy a lottery ticket or not. In your study of statistics, you will use the power of mathematics through probability calculations to analyze and interpret your data. Key term. In statistics, we generally want to study a population. You can think of a population as a collection of persons, things, or objects under study. To study the population, we select a sample. The idea of sampling is to select a portion or subset of the larger population and study that portion, the sample, to gain information about the population. Data are the result of sampling from a population. Because it takes a lot of time and money to examine an entire population, sampling is a very practical technique. If you wish to compute the overall grade point average at your school, it would make sense to select a sample of students who attend the school. The data collected from the sample would be the students' grade point averages. In presidential elections, opinion poll samples of 1,000,2,000 people are taken. The opinion poll is supposed to represent the views of the people in the entire country. Manufacturers of canned carbonated drinks take samples to determine if a 16-ounce can contain 16 ounces of carbonated drink. From the sample data, we can calculate a statistic. A statistic is a number that represents a property of the sample. For example, if we consider one math class to be a sample of the population of all math classes, then the average number of points earned by students in that one math class at the end of the term is an example of a statistic. The statistic is an estimate of a population parameter, in this case the mean. A parameter is a numerical characteristic of the whole population that can be estimated by a statistic. Since we considered all math classes to be the population, then the average number of points earned per student over all the math classes is an example of a parameter. One of the main concerns in the field of statistics is how accurately a statistic estimates a parameter. The accuracy really depends on how well the sample represents the population. The sample must contain the characteristics of the population in order to be a representative sample. We are interested in both the sample statistic and the population parameter in inferential statistics. In a later chapter, we will use the sample statistic to test the validity of the established population parameter. A variable or random variable, usually notated by capital letters such as x and y, is a characteristic or measurement that can be determined for each member of a population. Variables may be numerical or categorical. Numerical variables take on values with equal units such as weight in pounds and time in hours. Categorical variables place the person or thing into a category. If we let x equal the number of points earned by one math student at the end of a term, then x is a numerical variable. If we let y be a person's party affiliation, then some examples of y include Republican, Democrat, and Independent. Y is a categorical variable. We could do some math with values of x, calculate the average number of points earned, for example, but it makes no sense to do math with values of y. Calculating an average party affiliation makes no sense. Data are the actual values of the variable. They may be numbers or they may be words. Datum is a single value. Two words that come up often in statistics are mean and proportion. If you were to take 3 exams in your math classes and obtain scores of 86, 75, and 92, you would calculate your mean score by adding the 3 exam scores and dividing by 3. Your mean score would be 84. 3 to 1 decimal place. If in your math class there are 40 students and 22 are men and 18 are women, then the proportion of men students is 22:40, and the proportion of women students is 18:40. Mean and proportion are discussed in more detail in later chapters. Note: the words mean and average are often used interchangeably. The substitution of one word for the other is common practice. The technical term is arithmetic mean, and average is technically a center location. However, in practice among non-statisticians, average is commonly accepted for arithmetic mean. Example 1. Problem. Determine what the key terms refer to in the following study. We want to know the average, mean, amount of money first-year college students spend at ABC College on school supplies that do not include books. We randomly surveyed 100 first-year students at the college. 3 of those students spent $150, $200, and $225 respectively. Solution. The population is all first-year students attending ABC College this term. The sample could be all students enrolled in one section of a beginning statistics course at ABC College, although this sample may not represent the entire population. The parameter is the average, mean, amount of money spent excluding books by first-year college students at ABC College this term, the population mean. The statistic is the average, mean, amount of money spent excluding books by first-year college students in the sample. The variable could be the amount of money spent excluding books by one first-year student. Let x equals the amount of money spent excluding books by one first-year student attending ABC College. The data are the dollar amounts spent by the first-year students. Examples of the data are $150, $200, and $225. Try it 1. Determine what the key terms refer to in the following study. We want to know the average, mean, amount of money spent on school uniforms each year by families with children at Knoll Academy. We randomly survey 100 families with children in the school. 3 of the families spent $65, $75, and $95 respectively. Example 1. Problem. Determine what the key terms refer to in the following study. A study was conducted at a local college to analyze the average cumulative GPAs of students who graduated last year. Fill in the letter of the phrase that best describes each of the items below. 1. Population. 2. Statistic. 3. Parameter. 4. Sample. 5. Variable. 6. Date. All students who attended the college last year. The cumulative GPA of one student who graduated from the college last year. 3. 65, 280, 150, 390. A group of students who graduated from the college last year, randomly selected. The average cumulative GPA of students who graduated from the college last year. All students who graduated from the college last year. The average cumulative GPA of students in the study who graduated from the college last year. Solution 1. F2G3E4D5B6C. Try it 1-2. Determine what key terms refer to in the following study. A survey of athletes in a university was conducted to study the heights of athletes in meters. Fill in the letter of the phrase that best describes each of the items below. Population. Statistic. Parameter. Example. Variable. Data. The average height of athletes in the university. The average height of athletes in the survey. All athletes in the university. All students in the university. The height of one athlete. A group of athletes randomly selected. 182, 176, 169, 193. Example 1-3. Problem. Determine what the key terms refer to in the following study. As part of a study designed to test the safety of electric automobiles, the National Transportation Safety Board collected and reviewed data about the effects of an automobile crash on test dummies. Here is the criterion they used: speed at which cars crashed, location of drivers, i.e. dummies. 35 miles/hour front seat. Table 1-1. Cars with dummies in the front seats were crashed into a wall at a speed of 35 miles per hour. We want to know the proportion of dummies in the driver's seat that would have had head injuries if they had been actual drivers. We start with a simple random sample of 75 cars. Solution. The population is all cars containing dummies in the front seat. The sample is the 75 cars selected by a simple random sample. The parameter is the proportion of driver dummies if they had been real people who would have suffered head injuries in the population. The statistic is proportion of driver dummies if they had been real people who would have suffered head injuries in the sample. The variable x equals whether a dummy, if it had been a real person, would have suffered head injuries. The data are either yes, it had injury, or no, did not. Try it 1-3. Determine what the key terms refer to in the following study. A survey is conducted to check the time taken by a mobile for charging of battery from 50% to 100%. The criteria used to collect the data are wattage of charger used, type of mobile used. 30W Android. Table 1-2. We want to know the proportion of Android mobiles that are charged to 100% within 30 minutes. We start with a simple random sample of 200 mobiles. Example 1-4. Problem. Determine what the key terms refer to in the following study. An insurance company would like to determine the proportion of all medical doctors who have been involved in one or more malpractice lawsuits. The company selects 500 doctors at random from a professional directory and determines the number in the sample who have been involved in a malpractice lawsuit. Solution. The population is all medical doctors listed in the professional directory. The parameter is the proportion of medical doctors who have been involved in one or more malpractice suits in the population. The sample is the 500 doctors selected at random from the professional directory. The statistic is the proportion of medical doctors who have been involved in one or more malpractice suits in the sample. The variable x equals whether an individual doctor has been involved in a malpractice suit. The data are either yes, was involved in one or more malpractice lawsuits, or no, was not. Try it 1-4. Determine what the key terms refer to in the following study. A study is to be conducted by a news agency to find the proportion of all truck drivers that have no points on their license. The agency selects 1,000 truck drivers randomly from the directory of truck drivers and determines the number of truck drivers in the sample who have no points on their license. Collaborative exercise. Do the following exercise collaboratively with up to 4 people per group. Find a population, a sample, the parameter, the statistic, a variable, and data for the following study. You want to determine the average, mean number of glasses of milk college students drink per day. Suppose yesterday in your English class, you asked 5 students how many glasses of milk they drank the day before. The answers were 1, 0, 1, 3, and 4 glasses of milk. Data may come from a population or from a sample. Lowercase letters like x or y generally are used to represent data values. Most data can be put into the following categories: qualitative, quantitative. Qualitative data are the result of categorizing or describing attributes of a population. Qualitative data are also often called categorical data. Hair color, blood type, ethnic group, the car a person drives, and the street a person lives on are examples of qualitative categorical data. Qualitative categorical data are generally described by words or letters. For instance, hair color might be black, dark brown, light brown, blonde, gray, or red. Blood type might be AB plus, O, or B plus. Researchers often prefer to use quantitative data over qualitative categorical data because it lends itself more easily to mathematical analysis. For example, it does not make sense to find an average hair color or blood type. Quantitative data are always numbers. Quantitative data are the result of counting or measuring attributes of a population. Amount of money, pulse rate, weight, number of people living in your town, and number of students who take statistics are examples of quantitative data. Quantitative data may be either discrete or continuous. All data that are the result of counting are called quantitative discrete data. These data take on only certain numerical values. If you count the number of phone calls you receive for each day of the week, you might get values such as 0, 1, 2, or 3. Data that are not only made up of counting numbers, but that may include fractions, decimals, or irrational numbers, are called quantitative continuous data. Continuous data are often the results of measurements like lengths, weights, or times. A list of the lengths in minutes for all the phone calls that you make in a week, with numbers like 2, 4, 7, 5, or 11. 0 would be quantitative continuous data. Example 1, 5. Data sample of quantitative discrete data. The data are the number of books students carry in their backpacks. You sample 5 students. 2 students carry 3 books, 1 student carries 4 books, 1 student carries 2 books, and 1 student carries 1 book. The numbers of books 3, 4, 2, and 1 are the quantitative discrete data. Try it 1. The data are the number of machines in a gym. You sample 5 gyms. One gym has 12 machines, one gym has 15 machines, one gym has 10 machines, one gym has 22 machines, and the other gym has 20 machines. What type of data is this? Example 1.6. Data sample of quantitative continuous data. The data are the weights of backpacks with books in them. You sample the same 5 students. The weights in pounds of their backpacks are 6. 2, 7, 6, 8, 9, 1, 4, 3. Notice that backpacks carrying 3 books can have different weights. Weights are quantitative continuous data. Try it 1.6. The data are the areas of lawns in square feet. You sample 5 houses. The areas of the lawns are 144 sq feet, 160 sq feet, 190 sq feet, 180 sq feet, and 210 sq feet. What type of data is this? Example 1.7. You go to the supermarket and purchase 3 cans of soup, 19 ounces tomato bisque, 14. 1 ounces lentil and 19 ounces Italian wedding, 2 packages of nuts, walnuts, and peanuts, 4 different kinds of vegetable, broccoli, cauliflower, spinach, and carrots, and 2 desserts, 16 ounces pistachio ice cream, and 32 ounces chocolate chip cookies. Problem. Name data sets that are quantitative discrete, quantitative continuous, and qualitative categorical. Solution. 1 possible solution. The 3 cans of soup, 2 packages of nuts, 4 kinds of vegetables, and 2 desserts are quantitative discrete data because you count them. The weights of the soups 19 ounces, 14. 1 ounces, 19 ounces are quantitative continuous data because you measure weights as precisely as possible. Types of soups, nuts, vegetables, and desserts are qualitative, categorical data because they are categorical. Try to identify additional data sets in this example. Try it 1. 7. The following list of materials was purchased by a purchasing manager in a company. 2 types of nails, 2 kg box nails, 3 kg roofing nails. 1 type of oil, 4L machine oil. 4 types of screws, 3 kg wood screws, 5 kg machine screws, 1 kg set screws, 2 kg socket screws. Name data sets that are quantitative discrete, quantitative continuous, and qualitative. Example 1.8. The data are the colors of backpacks. Again, you sample the same 5 students. 1 student has a red backpack, 2 students have black backpacks, 1 student has a green backpack, and 1 student has a gray backpack. The colors red, black, green, and gray are qualitative, categorical data. Try it 1.8. The data are the colors of houses. You sample 5 houses. The colors of the houses are white, yellow, white, red, and white. What type of data is this? Note. You may collect data as numbers and report it categorically. For example, the quiz scores for each student are recorded throughout the term. At the end of the term, the quiz scores are reported as A, B, C, D, or F. Example 1. 9. Problem. Work collaboratively to determine the correct data type, quantitative or qualitative. Indicate whether quantitative data are continuous or discrete. Hint, data that are discrete often start with the words the number of. The number of pairs of shoes you own. The type of car you drive. The distance from your home to the nearest grocery store. The number of classes you take per school year. The type of calculator you use. Weights of dogs at an animal shelter. Number of correct answers on a quiz. IQ scores. This may cause some discussion. Solution. Items A, D, and G are quantitative discrete. Items C, F, and H are quantitative continuous. Items B and E are qualitative or categorical. Try it 1. 9. Determine the correct data type, quantitative or qualitative, for the number of cars in a parking lot. Indicate whether quantitative data are continuous or discrete. Example 1. Problem. A statistics professor collects information about the classification of her students as first-year students, sophomores, juniors, or seniors. The data she collects are summarized in the pie chart figure 1.2. What type of data does this graph show? This is a pie chart showing the class classification of statistics students. The chart has 4 sections labeled freshman, sophomore, junior, senior. A question is asked below the pie chart. What type of data does this graph show? Figure 1.2. Solution. This pie chart shows the students in each year, which is qualitative or categorical data. Try it 1. The registrar at State University keeps records of the number of credit hours students complete each semester. The data collected are summarized in the histogram. The class boundaries are 10 to less than 13, 13 to less than 16, 16 to less than 19, 19 to less than 22, and 22 to less than 25. This histogram consists of 5 bars with the x-axis marked at intervals of 3 from 10-25, and the y-axis in increments of 100 from 0-800. The height of bars shows the number of students in each interval, figure 1-3. What type of data does this graph show? Qualitative data discussion. Below are tables comparing the number of part-time and full-time students at De Anza College and Foothill College enrolled for the most recent spring quarter. The tables display counts, frequencies, and percentages or proportions, relative frequencies. The percent columns make comparing the same categories in the colleges easier. Displaying percentages along with the numbers is often helpful, but it is particularly important when comparing sets of data that do not have the same totals, such as the total enrollments for both colleges in this example. Notice how much larger the percentage for part-time students at Foothill College is compared to De Anza College. De Anza College, Foothill College. Number percent. Full-time 9, 240. 9% full-time 4, 0, 59, 28. 6%. Part-time 13, 296, 59. 1% part-time 10, 124, 71. 4%. Total 22, 496, 100% total 14. 183, 100%. Table 1. 3 most recent spring quarter. Tables are a good way of organizing and displaying data, but graphs can be even more helpful in understanding the data. There are no strict rules concerning which graphs to use. 2 graphs that are used to display qualitative, categorical data are pie charts and bar graphs. In a pie chart, categories of data are represented by wedges in a circle and are proportional in size to the percent of individuals in each category. In a bar graph, the length of the bar for each category is proportional to the number or percent of individuals in each category. Bars may be vertical or horizontal. A Pareto chart consists of bars that are sorted into order by category size, largest to smallest. Look at Figure 1.4 and Figure 1.5 and determine which graph, pie or bar, you think displays the comparisons better. It is a good idea to look at a variety of graphs to see which is the most helpful in displaying the data. We might make different choices of what we think is the best graph depending on the data and the context. Our choice also depends on what we are using the data for. Side-by-side pie charts showing the distribution of part-time and full-time students. The chart on the left is titled De Anza College. It is divided into 2 sections showing that part-time students represent 59% of the population and full-time students make up 49%. The chart on the right is titled Foothill College. It is divided into 2 sections showing that part-time students represent 71.4% of the population and full-time students make up 28.6%. Figure 1.4. A bar graph. The vertical axis marks values from 0% to 100% in intervals of 20%. The horizontal axis categories are under age 25, height of bar shows 61. 0% intend to transfer, height of bar shows 48. 6% full-time, height of bar shows 40. 9% and all students, height of bar shows 100%, figure 1. Percentages that add to more or less than 100%. Sometimes percentages add up to be more than 100% or less than 100%. In the graph, the percentages add to more than 100% because students can be in more than one category. A bar graph is appropriate to compare the relative size of the categories. A pie chart cannot be used. It also could not be used if the percentages added to less than 100%. Characteristic/category percent. Full-time students 49%. Students who intend to transfer to a 4-year educational institution 48. 6%. Students under age 25 61, 0%. Total 155%. Table 1 for De Anza College most recent spring quarter. A bar graph. The vertical axis marks values from 0% to 100% in intervals of 20%. The horizontal axis categories are under age 25, height of bar shows 61. 0% intend to transfer, height of bar shows 48. 6% full-time, height of bar shows 40. 9% and all students, height of bar shows 100%, figure 1. Omitting categories, missing data. The table displays ethnicity of students, but is missing the other unknown category. This category contains people who did not feel they fit into any of the ethnicity categories or declined to respond. Notice that the frequencies do not add up to the total number of students. In this situation, create a bar graph and not a pie chart. Frequency percent. Asian 8, 794, 36. 1%. Black 1, 412, 5, 8%. Filipino 1, 298, 5, 3%. Hispanic/Latino 4, 180, 17. 1%. Native American 146, 0, 6%. Pacific Islander 236, 1, 0%. White 5, 978, 24. 5%. Total 22, 0, 44 out of 24, 382, 90. 4% out of 100%. Table 1. 5 ethnicity of students at De Anza College in the most recent fall term. A bar graph showing ethnicity of students. The vertical axis marks values from 0% to 40, 0% in intervals of 5. 0%. The horizontal axis categories are Asian height of bar shows 36 1%, Black height of bar shows 5 8%, Filipino height of bar shows 5 3%, Hispanic Latino height of bar shows 17 1%, Native American height of bar shows 0.6%, Pacific Islander height of bar shows 1.0%, and white height of bar shows 24.5%, figure 1.7. The following graph is the same as the previous graph, but the other unknown percent 96% has been included. The other unknown category is large compared to some of the other categories: Native American, 0.6%, Pacific Islander, 1.0%. This is important to know when we think about what the data are telling us. This particular bar graph in Figure 1.8 can be difficult to understand visually. The graph in Figure 1.9 is a Pareto chart. The Pareto chart has the bars sorted from largest to smallest and is easier to read and interpret. Bar graph consisting of 8 bars with values matching the given data. Horizontal axis has all ethnicity of student. Vertical axis ranges F from 0 to 40% in increments of 5%, Figure 1. 8 bar graph with other unknown category. A bar graph showing ethnicity of students. The vertical axis marks values from 0% to 40, 0% in intervals of 5-0%. The horizontal axis categories are Asian height of bar shows 36 1%, Black height of bar shows 5 8%, Filipino height of bar shows 5 3%, Hispanic Latino height of bar shows 17 1%, Native American height of bar shows 0.6%, Pacific Islander height of bar shows 1.0%, and white height of bar shows 24.5%. Figure 1.9 Pareto chart with bars sorted by size. Pie charts, no missing data. The following pie charts have the other unknown category included, since the percentages must add to 100%. The chart in Figure 1.10b is organized by the size of each wedge, which makes it a more visually informative graph than the unsorted alphabetical graph in Figure 1.10a. 2 pie charts are titled Ethnicity of Students. Chart A, the sections of the chart are ordered alphabetically. Clockwise from the top, the sections show that Asian students make up 36.1% of students, Black 5.8%, Filipino 5.3%, Hispanic 17.1%, Native American 0.6%, Pacific Islander 1.0%, White 24.5%, and other 9.6%. Chart B, this is the same data as shown in Chart A, but the sections of the chart are now ordered from greatest area to least. Clockwise from the top, the sections show that Asian students make up 36.1% of students, White 24.5%, Hispanic 17.1%, other 9.6%, Black 5.8%, Filipino 5.3%, Pacific Islander 1.0%, and Native American 0.6%, Figure 1.10. Sampling. Gathering information about an entire population often costs too much or is virtually impossible. Instead, we use a sample of the population. A sample should have the same characteristics as the population it is representing. Most statisticians use various methods of random sampling in an attempt to achieve this goal. This section will describe a few of the most common methods. There are several different methods of random sampling. In each form of random sampling, each member of a population initially has an equal chance of being selected for the sample. Each method has pros and cons. The easiest method to describe is called a simple random sample. Any group of n individuals is equally likely to be chosen as any other group of n individuals if the simple random sampling technique is used. In other words, each sample of the same size has an equal chance of being selected. Besides simple random sampling, there are other forms of sampling that involve a chance process for getting the sample. Other well-known random sampling methods are the stratified sample, the cluster sample, and the systematic sample. To choose a stratified sample, divide the population into groups called strata and then take a proportionate number from each stratum. For example, you could group your college population by department and then choose a proportionate simple random sample from each stratum, each department, to get a stratified random sample. To choose a simple random sample from each department, number each member of the first department, number each member of the second department, and do the same for the remaining departments. Then use simple random sampling to choose proportionate numbers from the first department and do the same for each of the remaining departments. Those numbers picked from the first department, picked from the second department, and so on represent the members who make up the stratified sample. To choose a cluster sample, divide the population into clusters groups and then randomly select some of the clusters. All the members from these clusters are in the cluster sample. For example, if you randomly sample 4 departments from your college population, the 4 departments make up the cluster sample. Divide your college faculty by department. The departments are the clusters. Number each department and then choose 4 different numbers using simple random sampling. All members of the 4 departments with those numbers are the cluster sample. To choose a systematic sample, randomly select a starting point and take every nth piece of data from a listing of the population. For example, suppose you have to do a phone survey. Your phone book contains 20,000 residence listings. You must choose 400 names for the sample. Number the population 120,000 and then use a simple random sample to pick a number that represents the first name in the sample. Then choose every 50th name thereafter until you have a total of 400 names. You might have to go back to the beginning of your phone list. Systematic sampling is frequently chosen because it is a simple method. A type of sampling that is non-random is convenience sampling. Convenience sampling involves using results that are readily available. For example, a computer software store conducts a marketing study by interviewing potential customers who happen to be in the store browsing through the available software. The results of convenience sampling may be very good in some cases and highly biased, favor certain outcomes in others. Sampling data should be done very carefully. Collecting data carelessly can have devastating results. Surveys mailed to households and then returned may be very biased. They may favor a certain group. It is better for the person conducting the survey to select the sample respondents. True random sampling is done with replacement. That is, once a member is picked, that member goes back into the population and thus may be chosen more than once. However, for practical reasons, in most populations, simple random sampling is done without replacement. Surveys are typically done without replacement. That is, a member of the population may be chosen only once. Most samples are taken from large populations, and the sample tends to be small in comparison to the population. Since this is the case, sampling without replacement is approximately the same as sampling with replacement, because the chance of picking the same individual more than once with replacement is very low. Sampling without replacement instead of sampling with replacement becomes a mathematical issue only when the population is small. When you analyze data, it is important to be aware of sampling errors and non-sampling errors. The actual process of sampling causes sampling errors. For example, the sample may not be large enough. Factors not related to the sampling process cause non-sampling errors. A defective counting device can cause a non-sampling error. In reality, a sample will never be exactly representative of the population, so there will always be some sampling error. As a rule, the larger the sample, the smaller the sampling error. In statistics, a sampling bias is created when a sample is collected from a population, and some members of the population are not as likely to be chosen as others. Remember, each member of the population should have an equally likely chance of being chosen. When a sampling bias happens, there can be incorrect conclusions drawn about the population that is being studied. Critical evaluation. We need to evaluate the statistical studies we read about critically and analyze them before accepting the results of the studies. Common problems to be aware of include problems with samples. A sample must be representative of the population. A sample that is not representative of the population is biased. Biased samples that are not representative of the population give results that are inaccurate and not valid. Self-selected samples. Responses only by people who choose to respond, such as call-in surveys, are often unreliable. Sample size issues. Samples that are too small may be unreliable. Larger samples are better if possible. In some situations, having small samples is unavoidable and can still be used to draw conclusions. Examples: crash testing cars or medical testing for rare conditions. Undue influence, collecting data or asking questions in a way that influences the response. Non-response or refusal of subject to participate. The collected responses may no longer be representative of the population. Often, people with strong positive or negative opinions may answer surveys, which can affect the results. Causality. A relationship between two variables does not mean that one causes the other to occur. They may be related, correlated, because of their relationship through a different variable. Self-funded or self-interest studies. A study performed by a person or organization in order to support their claim. Is the study impartial? Read the study carefully to evaluate the work. Do not automatically assume that the study is good, but do not automatically assume the study is bad either. Evaluate it on its merits and the work done. Misleading use of data, improperly displayed graphs, incomplete data, or lack of context. Confounding, when the effects of multiple factors on a response cannot be separated. Confounding makes it difficult or impossible to draw valid conclusions about the effect of each factor. Example 111. Problem. A study is done to determine the average tuition that San Jose State undergraduate students pay per semester. Each student in the following samples is asked how much tuition they paid for the fall semester. What is the type of sampling in each case? A sample of 100 undergraduate San Jose State students is taken by organizing the students' names by classification, first-year student, sophomore, junior, or senior, and then selecting 25 students from each. A random number generator is used to select a student from the alphabetical listing of all undergraduate students in the fall semester. Starting with that student, every 50th student is chosen until 75 students are included in the sample. A completely random method is used to select 75 students. Each undergraduate student in the fall semester has the same probability of being chosen at any stage of the sampling process. The first year, sophomore, junior, and senior years are numbered 1, 2, 3, and 4, respectively. A random number generator is used to pick 2 of those years. All students in those 2 years are in the sample. An administrative assistant is asked to stand in front of the library one Wednesday and to ask the first 100 undergraduate students. He encounters what they paid for tuition the fall semester. Those 100 students are the sample. Try it 111. You are going to use the random number generator to generate different types of samples from the data. This table displays 6 sets of quiz scores. Each quiz counts 10 points for an elementary statistics class. 1, 2, 3, 4, 5, 6, 5, 7, 10, 9, 8, 3, 10, 5, 9, 8, 7, 6, 9, 10, 8, 6, 7, 9, 9, 10, 10, 9, 8, 9, 7, 8, 9, 5, 7, 4, 9, 9, 9, 10, 8, 7, 7, 7, 10, 9, 8, 8, 8, 8, 9, 10, 8, 8, 9, 7, 8, 7, 7, 8, 8, 8, 10, 9, 8, 7. Table 1. Instructions: use the random number generator to pick samples. Create a stratified sample by column. Pick 3 quiz scores randomly from each column. Number each row 1 through 10. On your calculator, press Math and arrow over to PRB. For column 1, press 5 rand int and enter 110. Press enter, record the number. Press enter 2 more times, even the repeats. Record these numbers. Record the 3 quiz scores in column 1 that correspond to these 3 numbers. Repeat for columns 2 through 6. These 18 quiz scores are a stratified sample. Create a cluster sample by picking 2 of the columns. Use the column numbers 1 through 6. Press Math and arrow over to PRB. Press 5 rand int and enter 16. Press enter, record the number. Press enter and record that number. The 2 numbers are for 2 of the columns. The quiz scores, 20 of them in these 2 columns, are the cluster sample. Create a simple random sample of 15 quiz scores. Use the numbering 1 through 60. Press Math, arrow over to PRB. Press 5 rand int and enter 160. Press enter 15 times and record the numbers. Record the quiz scores that correspond to these numbers. These 15 quiz scores are the random sample. Create a systematic sample of 12 quiz scores. Use the numbering 1 through 60. Press Math, arrow over to PRB. Press 5 rand int and enter 160. Press enter, record the number and the first quiz score. From that number, count 10 quiz scores and record that quiz score. Keep counting 10 quiz scores and recording the quiz score until you have a sample of 12 quiz scores. You may wrap around, go back to the beginning. Example 1. Problem. Determine the type of sampling used: simple, random, stratified, systematic, cluster, or convenience. A soccer coach selects 6 players from a group of boys aged 8 to 10, 7 players from a group of boys aged 11 to 12, and 3 players from a group of boys aged 13 to 14 to form a recreational soccer team. A pollster interviews all human resource personnel in 5 different high-tech companies. A high school educational researcher interviews 50 public high school teachers and 50 private high school teachers. A medical researcher interviews every 3rd cancer patient from a list of cancer patients at a local hospital. A high school counselor uses a computer to generate 50 random numbers and then picks students whose names correspond to the numbers. A student interviews classmates in their algebra class to determine how many pairs of genes a student owns on the average. Solution: A stratified, B cluster, C stratified, D systematic, E simple, random, F convenient. Try it 112. Determine the type of sampling used: simple, random, stratified, systematic, cluster, or convenience. A high school principal polls 50 first-year students, 50 sophomores, 50 juniors, and 50 seniors regarding policy changes for after-school activities. If we were to examine two samples representing the same population, even if we used random sampling methods for the samples, they would not be exactly the same. Just as there is variation in data, there is variation in samples. As you become accustomed to sampling, the variability will begin to seem natural. Note: in confidence intervals of the text, sample size formulas are provided which will determine sample sizes when sampling from a population. The sample size will be a function of the desired precision and not a function of the population size. It may be somewhat counterintuitive that the sample size does not depend on the population size. However, this implies that a sample size of 1,000 can be adequate to represent a population of 100,000 versus 1 million, given that the same level of precision is desired. When working in confidence intervals with sample size formulas, the student will notice that population size is not a factor in determining the sample size. Example 1. 13. Suppose ABC College has 10,000 part-time students, the population. We are interested in the average amount of money a part-time student spends on books in the fall term. Asking all 10,000 students is an almost impossible task. Suppose we take two different samples. First, we use convenience sampling and survey 10 students from a first-term organic chemistry class. Many of these students are taking first-term calculus in addition to the organic chemistry class. The amount of money they spend on books is as follows: $128, $87, $173, $116, $130, $204, $147, $189, $93, $153. The second sample is taken using a list of senior citizens who take PE classes and taking every fifth senior citizen on the list for a total of 10 senior citizens. They spend $50. $40, $36, $15, $50, $100, $40, $53, $22, $22. It is unlikely that any student is in both samples. Problem. Do you think that either of these samples is representative of, or is characteristic of the entire 10,000 part-time student population? Solution. A. No, the first sample probably consists of science-oriented students. Besides the chemistry course, some of them are also taking first-term calculus. Books for these classes tend to be expensive. Most of these students are, more than likely, paying more than the average part-time student for their books. The second sample is a group of senior citizens who are, more than likely, taking courses for health and interest. The amount of money they spend on books is probably much less than the average part-time student. Both samples are biased. Also, in both cases, not all students have a chance to be in either sample. Problem. B. Since these samples are not representative of the entire population, is it wise to use the results to describe the entire population? Solution. B. No, for these samples, each member of the population did not have an equally likely chance of being chosen. Now, suppose we take a third sample. We choose 10 different part-time students from the disciplines of chemistry, math, English, psychology, sociology, history, nursing, physical education, art, and early childhood development. We assume that these are the only disciplines in which part-time students at ABC College are enrolled, and that an equal number of part-time students are enrolled in each of the disciplines. Each student is chosen using simple random sampling. Using a calculator, random numbers are generated, and a student from a particular discipline is selected if they have a corresponding number. The students spend the following amounts: $180, $50, $150, $85, $260, $75, $180, $200, $200, $150. Problem. C is the sample biased. Solution. C. The sample is unbiased, but a larger sample would be recommended to increase the likelihood that the sample will be close to representative of the population. However, for a biased sampling technique, even a large sample runs the risk of not being representative of the population. Students often ask if it is good enough to take a sample instead of surveying the entire population. If the survey is done well, the answer is yes. Try it. 113. A local radio station has a fan base of 20,000 listeners. The station wants to know if its audience would prefer more music or more talk shows. Asking all 20,000 listeners is an almost impossible task. The station uses convenience sampling and surveys the first 200 people they meet at one of the station's music concert events. 24 people said they'd prefer more talk shows, and 176 people said they'd prefer more music. Do you think that this sample is representative of, or is characteristic of, the entire 20,000 listener population? Variation in data. Variation is present in any set of data. For example, 16-ounce cans of beverage may contain more or less than 16 ounces of liquid. In one study, 8 16-ounce cans were measured and produced the following amount in ounces of beverage: 15.8, 16.1, 15.2, 14.8, 15.8, 15.9, 16.0, 15. Measurements of the amount of beverage in a 16-ounce can may vary because different people make the measurements, or because the exact amount, 16 ounces of liquid, was not put into the cans. Manufacturers regularly run tests to determine if the amount of beverage in a 16-ounce can falls within the desired range. Be aware that as you take data, your data may vary somewhat from the data someone else is taking for the same purpose. This is completely natural. However, if two or more of you are taking the same data and get very different results, it is time for you and the others to reevaluate your data-taking methods and your accuracy. Variation in samples. It was mentioned previously that two or more samples from the same population, taken randomly, and having close to the same characteristics of the population will likely be different from each other. Suppose Dorian and Jung both decide to study the average amount of time students at their college sleep each night. Dorian and Jung each take samples of 500 students. Dorian uses systematic sampling and Jung uses cluster sampling. Dorian's sample will be different from Jung's sample. Even if Dorian and Jung used the same sampling method, in all likelihood their samples would be different. Neither would be wrong, however. Think about what contributes to making Dorian's and Jung's samples different. If Dorian and Jung took larger samples, i.e. the number of data values is increased, their sample results, the average amount of time a student sleeps, might be closer to the actual population average. But still, their samples would be in all likelihood different from each other. This variability in samples cannot be stressed enough. Size of a sample. The size of a sample, often called the number of observations, usually given the symbol n, is important. The examples you have seen in this book so far have been small. Samples of only a few hundred observations, or even smaller, are sufficient for many purposes. In polling, samples that are from 1,200 to 1,500 observations are considered large enough and good enough if the survey is random and is well done. Later we will find that even much smaller sample sizes will give very good results. You will learn why when you study confidence intervals. Be aware that many large samples are biased. For example, call-in surveys are invariably biased because people choose to respond or not. Once you have a set of data, you will need to organize it so that you can analyze how frequently each datum occurs in the set. However, when calculating the frequency, you may need to round your answers so that they are as precise as possible. Levels of measurement. The way a set of data is measured is called its level of measurement. Correct statistical procedures depend on a researcher being familiar with levels of measurement. Not every statistical operation can be used with every set of data. Data can be classified into 4 levels of measurement. They are from lowest to highest level. Nominal scale level, ordinal scale level, interval scale level, ratio scale level. Data that is measured using a nominal scale is qualitative categorical. Categories, colors, names, labels, and favorite foods along with yes or no responses are examples of nominal level data. Nominal scale data are not ordered. For example, trying to classify people according to their favorite food does not make any sense. Putting pizza first and sushi second is not meaningful. Smartphone companies are another example of nominal scale data. The data are the names of the companies that make smartphones, but there is no agreed upon order of these brands, even though people may have personal preferences. Nominal scale data cannot be used in calculations. Data that is measured using an ordinal scale is similar to nominal scale data, but there is a big difference. The ordinal scale data can be ordered. An example of ordinal scale data is a list of the top 5 national parks in the United States. The top 5 national parks in the United States can be ranked from 1 to 5, but we cannot measure differences between the data. Another example of using the ordinal scale is a cruise survey where the responses to questions about the cruise are excellent, good, satisfactory, and unsatisfactory. These responses are ordered from the most desired response to the least desired, but the differences between two pieces of data cannot be measured. Like the nominal scale data, ordinal scale data cannot be used in calculations. Data that is measured using the interval scale is similar to ordinal level data because it has a definite ordering, but there is a difference between data. The differences between interval scale data can be measured, though the data does not have a starting point. Temperature scales like Celsius C and Fahrenheit F are measured by using the interval scale. In both temperature measurements, 40 degrees is equal to 100 degrees minus 60 degrees. Differences make sense. But 0 degrees does not, because in both scales, 0 is not the absolute lowest temperature. Temperatures like degrees F and minus 15 degrees C exist and are colder than 0. Interval level data can be used in calculations, but one type of comparison cannot be done. 80 degrees C is not 4 times as hot as 20 degrees C, nor is 80 degrees F 4 times as hot as 20 degrees F. There is no meaning to the ratio of 80 to 20 or 4 to 1. Data that is measured using the ratio scale takes care of the ratio problem and gives you the most information. Ratio scale data is like interval scale data, but it has a 0 point and ratios can be calculated. For example, 4 multiple choice statistics final exam scores are 80, 68, 20, and 92 out of a possible 100 points. The exams are machine graded. The data can be put in order from lowest to highest, 20, 68, 80, 92. The differences between the data have meaning. The score 92 is more than the score 68 by 24 points. Ratios can be calculated. The smallest score is 0, so 80 is 4 times 20. The score of 80 is 4 times better than the score of 20. Frequency 20 students were asked how many hours they worked per day. Their responses in hours are as follows: 5, 6, 3, 3, 2, 4, 7, 5, 2, 3. 5, 6, 5, 4, 4, 3, 5, 2, 5, 3. Table 17 lists the different data values in ascending order and their frequencies. Data value frequency 23354356627 Table 1. 7 Frequency table of student work hours of frequency is the number of times a value of the data occurs. According to Table 17, there are 3 students who work 2 hours, 5 students who work 3 hours, and so on. The sum of the values in the frequency column 20 represents the total number of students included in the sample. A relative frequency is the ratio, fraction, or proportion of the number of times a value of the data occurs in the set of all outcomes to the total number of outcomes. To find the relative frequencies, divide each frequency by the total number of students in the sample, in this case 20. Relative frequencies can be written as fractions, percents, or decimals. Data value frequency relative frequency 23320 or 0, 1535520 or 0. 25,43320 or 0, 15,56620 or 0. 36,2220 or 0. 10,71120 or 0. 5 Table 18 Frequency table of student work hours with relative frequencies. The sum of the values in the relative frequency column of Table 1. 8 is 2020, or 1 cumulative relative frequency is the accumulation of the previous relative frequencies. To find the cumulative relative frequencies, add all the previous relative frequencies to the relative frequency for the current row, as shown in Table 1. 9. Data value frequency relative frequency cumulative relative frequency 23320 or 0, 15, 0, 15, 35520 or 0, 25, 0, 15 plus 0. 25 equals 0, 44, 3320 or 0, 15, 0, 40 plus 0, 15 equals 0, 55, 5, 6, 6, 20 or 0, 30, 0. 55 plus 0. 30 equals 0. 85 6 2 2 20 or 0 10 0. 85 plus 0 10 equals 0. 95 7 1 1 20 or 0 5 0 95 plus 0. 5 equals 1 Table 19 Frequency table of student work hours with relative and cumulative relative frequencies. The last entry of the cumulative relative frequency column is 1, indicating that 100% of the data has been accumulated. Note, because of rounding, the relative frequency column may not always sum to 1, and the last entry in the cumulative relative frequency column may not be 1. However, they each should be close to 1. Table 1. 10 represents the heights in inches of a sample of 100 semi-professional soccer players. Heights, inches, frequency, relative frequency, cumulative relative frequency 59, 95, 61. 95, 5, 5, 100 equals 0. 50, 561, 95, 63, 95, 33, 100 equals 0, 30, 5 plus 0. 3 equals 0, 863, 95, 65, 95, 15, 15, 100 equals 0, 15, 0, 8 plus 0, 15 equals 0, 23, 65. 95, 67, 95, 40, 40, 100 equals 0, 40, 0, 23 plus 0, 40 equals 0, 63, 67, 95, 69. 95, 17, 17, 100 equals 0, 17, 0. 63 plus 0, 17 equals 0. 80, 69, 95, 71. 95, 12, 12, 100 equals 0, 12, 0. 80 plus 0, 12 equals 0. 92, 71, 95, 73, 95, 7, 7, 100 equals 0. 7, 0, 92 plus 0, 7 equals 0. 99, 73, 95, 75, 95, 1, 1, 100 equals 0. 1, 0, 99 plus 0. 1 equals 1 total equals 100 total equals 1 Table 110 Frequency table of soccer player height. The data in this table have been grouped into the following intervals: 59, 95 to 61, 95 inches 61, 95 to 63, 95 inches 63, 95 to 65, 95 inches 65, 95 to 67. 95 inches 67, 95 to 69, 95 inches 69, 95 to 71, 95 inches 71, 95 to 73, 95 inches 73, 95 to 75. 95 inches in this sample, there are 5 players whose heights fall within the interval 59, 95 61, 95 inches, 3 players whose heights fall within the interval 61, 95 63, 95 inches, 15 players whose heights fall within the interval 63, 95 65, 95 inches, 40 players whose heights fall within the interval 65, 95 67, 95 inches, 17 players whose heights fall within the interval 67, 95 69, 95 inches, 12 players whose heights fall within the interval 69, 95 71, 95 7 players whose heights fall within the interval 71, 95 73, 95 and 1 player whose heights fall within the interval 73, 95 75, 95. All heights fall between the endpoints of an interval and not at the endpoints. Example 114 problem from Table 110, find the percentage of heights that are less than 65. 95 inches, try it 1. 14 Table 111 shows the amount in inches of annual rainfall in a sample of towns. Rainfall inches frequency relative frequency cumulative relative frequency 2. 95 4, 97 6 650 equals 0 12 0. 12 4, 97 6, 99 7 750 equals 0 14 0 12 plus 0 14 equals 0. 26 6, 99 9, 1 15 15 50 equals 0 30 0. 26 plus 0 30 equals 0. 56 9, 0 1 11 3 8 8 50 equals 0. 16 0, 56 plus 0 16 equals 0 72 11, 0 3 13. 599 50 equals 0 18 0 72 plus 0 18 equals 0. 90 13, 0 5 15. 755 50 equals 0 10 0 90 plus 0 10 equals 1 total equals 50 total equals 1 Table 1. 11 from Table 111, find the percentage of rainfall that is less than 91 inches. Example 115 problem from Table 110, find the percentage of heights that fall between 61, 95 and 65 95 inches. Try it 115 from Table 111, find the percentage of rainfall that is between 699 and 13, 5 inches, example 1. 16 problem, use the heights of the 100 semi-professional soccer players in Table 110, fill in the blanks and check your answers. The percentage of heights that are from 67, 95 to 71. 95 inches is, the percentage of heights that are from 67, 95 to 73, 95 inches is, the percentage of heights that are more than 65, 95 inches is. The number of players in the sample who are between 61 95 and 71, 95 inches tall is, what kind of data are the heights? Describe how you could gather this data, the heights, so that the data are characteristic of all semi-professional soccer players. Remember, you count frequencies. To find the relative frequency, divide the frequency by the total number of data values. To find the cumulative relative frequency, add all of the previous relative frequencies to the relative frequency for the current row. Solution 29%, 36%, 77%, 87. Quantitative continuous. Get rosters from each team and choose a simple random sample from each try at 116 from Table 1. 11. Find the number of towns that have rainfall between 295 and 91 inches. Collaborative exercise in your class. Have someone conduct a survey of the number of siblings each student has. Create a frequency table. Add to it a relative frequency column and a cumulative relative frequency column. Answer the following questions. What percentage of the students in your class have no siblings? What percentage of the students have from 1 to 3 siblings? What percentage of the students have fewer than 3 siblings? Example 117 19 people were asked how many miles to the nearest mile they commute to work each day. The data are as follows: 2 5 7 3 2 10 18 15 27 10 18 5 12 13 12 4 5 10. Table 112 was produced. Data frequency, relative frequency, cumulative relative frequency. 2 2 2 19 2 19 3 1 1 19 3 19 4 1 1 19 4 19 5 3 3 19 7 19 7 2 2 19 9 19 10 3 3 19 12 19 12 2 2 19 14 19 13 1 1 19 15 19 15 1 1 19 16 19 18 1 1 19 17 19 21 1 19 19 19 Table 1. 12 Frequency of commuting distances problem. Is the table correct? If it is not correct, what is wrong, true or false? 3% of the people surveyed commute 3 miles or less. If the statement is not correct, what should it be? If the table is incorrect, make the corrections. What fraction of the people surveyed commute 5 or 7 miles? What fraction of the people surveyed commute 12 miles or more, less than 12 miles? Between 5 and 13 miles, not including 5 and 13 miles. The cumulative relative frequency column should read 219, 319, 419, 719, 919, 1219, 1419, 1519, 1619, 1819, 1919. Solution: no. The frequency column sums to 18, not 19. Not all cumulative relative frequencies are correct. False. The frequency for 3 miles is 1, for 2 miles 2. 519, 719, 1219, 719. Try it 1. 17. Table 111 represents the amount, in inches, of annual rainfall in a sample of towns. What fraction of towns surveyed get between 11, 3 and 13, 5 inches of rainfall each year? Example 118. Table 113 contains data for the number of years of service for 70 federal employees. Number of years of service. Number of federal employees: 24 2, 25 1, 26 3, 27 0, 28 4, 29 6, 30 11 31 12 32 7 33 8 34 6 35 10. Table 113. Problem: answer the following questions. What is the cumulative frequency for years of service between 30 and 35, inclusive? What is the relative frequency for 30 years of service? What is the relative frequency for 30 years of service or less? What is the relative frequency for 25 years of service or more? Solution: cumulative frequency is 54, 1170 or 0. 157 or 15.7%, 2770 or 0, 386 or 38. 6%, 6870 or 0, 971 or 97. 1%. Try it 1. 18. Table 114 contains the total number of fatal motor vehicle traffic crashes in the United States for a period of 18 years. Year: total number of crashes. Year: total number of crashes. Year: 136, 254. Year: 1138, 444. Year: 237, 241. Year: 1239, 252. Year: 337, 494. Year: 1338, 648. Year: 437, 324. Year: 1437, 435. Year: 537, 107. Year: 1534, 172. Year: 637, 140. Year: 1630, 862. Year: 737, 526. Year: 1730, 296. Year: 837, 862. Year: 1829, 757. Year: 938, 491. Total 653, 782. Year: 1038, 477. Table 114. Answer the following questions. What is the frequency of deaths measured from year 7 through year 11? What percentage of deaths occurred after year 13? What is the relative frequency of deaths that occurred in year 7 or before? What is the percentage of deaths that occurred in year 18? What is the cumulative relative frequency for year 13? Explain what this number tells you about the data. Does aspirin reduce the risk of heart attacks? Is one brand of fertilizer more effective at growing roses than another? Is fatigue as dangerous to a driver as the influence of alcohol? Questions like these are answered using randomized experiments. In this module, you will learn important aspects of experimental design. Proper study design ensures the production of reliable, accurate data. The purpose of an experiment is to investigate the relationship between two variables. When one variable causes change in another, we call the first variable the independent variable or explanatory variable. The affected variable is called the dependent variable or response variable. Stimulus, response. In a randomized experiment, the researcher manipulates values of the explanatory variable and measures the resulting changes in the response variable. The different values of the explanatory variable are called treatments. An experimental unit is a single object or individual to be measured. You want to investigate the effectiveness of vitamin E in preventing disease. You recruit a group of subjects and ask them if they regularly take vitamin E. You notice that the subjects who take vitamin E exhibit better health on average than those who do not. Does this prove that vitamin E is effective in disease prevention? It does not. There are many differences between the two groups compared in addition to vitamin E consumption. People who take vitamin E regularly often take other steps to improve their health. Exercise, diet, other vitamin supplements, choosing not to smoke. Any one of these factors could be influencing health. As described, this study does not prove that vitamin E is the key to disease prevention. Additional variables that can cloud a study are called lurking variables. In order to prove that the explanatory variable is causing a change in the response variable, it is necessary to isolate the explanatory variable. The researcher must design her experiment in such a way that there is only one difference between groups being compared: the planned treatments. This is accomplished by the random assignment of experimental units to treatment groups. When subjects are assigned treatments randomly, all of the potential lurking variables are spread equally among the groups. At this point, the only difference between groups is the one imposed by the researcher. Different outcomes measured in the response variable, therefore, must be a direct result of the different treatments. In this way, an experiment can prove a cause-and-effect connection between the explanatory and response variables. The power of suggestion can have an important influence on the outcome of an experiment. Studies have shown that the expectation of the study participant can be as important as the actual medication. In one study of performance-enhancing drugs, researchers noted, results showed that believing one had taken the substance resulted in performance times almost as fast as those associated with consuming the drug itself. In contrast, taking the drug without knowledge yielded no significant performance increment. McClung, M. Collins D. Because I Know It Will, Placebo Effects of an Ergogenic Aid on Athletic Performance. Journal of Sport and Exercise Psychology. 2007, Jun 29 380-294, Web, April 30, 2013. When participation in a study prompts a physical response from a participant, it is difficult to isolate the effects of the explanatory variable. To counter the power of suggestion, researchers set aside one treatment group as a control group. This group is given a placebo treatment, an active treatment that cannot directly influence the response variable. The control group helps researchers balance the effects of being in an experiment with the effects of the active treatments. Of course, if you are participating in a study and you know that you are receiving a pill which contains no actual medication, then the power of suggestion is no longer a factor. Blinding or masking in a randomized experiment preserves the power of suggestion. When a person involved in a research study is blinded, they don't know who is receiving the active treatment S and who is receiving the placebo treatment. A double-blind experiment is one in which both the subjects and the researchers involved with the subjects are blinded. Example 119 problem: the Smell and Taste Treatment and Research Foundation conducted a study to investigate whether smell can affect learning. Subjects completed mazes multiple times while wearing masks. They completed the pencil and paper mazes 3 times wearing floral-scented masks and 3 times with unscented masks. Participants were assigned at random to wear the floral mask during the first 3 trials or during the last 3 trials. For each trial, researchers recorded the time it took to complete the maze and the subject's impression of the mask scent. Positive, negative, or neutral. Describe the explanatory and response variables in this study. What are the treatments? Identify any lurking variables that could interfere with this study. Is it possible to use blinding in this study? Solution: the explanatory variable is scent and the response variable is the time it takes to complete the maze. There are 2 treatments, a floral-scented mask and an unscented mask. All subjects experienced both treatments. The order of treatments was randomly assigned, so there were no differences between the treatment groups. Random assignment eliminates the problem of lurking variables. Subjects will clearly know whether they can smell flowers or not, so subjects cannot be blinded in this study. Researchers timing the mazes can be blinded, though. The researcher who is observing a subject will not know which mask is being worn. Try it 119. The placebo research group conducted a study to find the extent of placebo effects. A group of people randomly selected were asked to take a test before and after taking a pill that induces a mild headache. The pill in half of the randomly selected people was replaced with a similar pill that has no effect. For each trial, researchers recorded the change in time people took to complete the tests before and after taking the pill. Describe the explanatory and response variable in this study. What are the treatments? Identify any lurking variables that could interfere with this study. Is it possible to use blinding in this study?